You've bought some new LED fixtures to replace your tungsten generics, and you're going to install them in your venue. You just need to plug them in, and off you go, unlocking all that creative potential just burning inside you. Right? Right? Well, almost. I'm here to suggest that you stop and take a breath and think a little about where you're going to plug them in, what features of LEDs might affect that decision, and why planning your power control and infrastructure now could just save your show. So, what questions do you need to ask yourself? How many fixtures can I put on one circuit? Which is very quickly replaced with, how many fixtures should I put on a circuit? And most importantly, what happens when something goes wrong? How many fixtures you can pull in a circuit is reasonably straightforward to answer. Like with the tungsten fixtures you're used to, it starts with the current draw of the fixture. You can find it on the datasheet, and the capacity of the circuit that you're plugging it into. But there are a couple of complications to think about for LEDs compared to tungsten. As many of you will already know, intelligent fixtures like LEDs and moving lights mostly can't be connected directly to a dimmer, and instead need unadulterated hard mains power. I say mostly as there are a couple of exceptions, one of which is our fixed white source forwards, which can be line dimmed on a standard dimmer just like a tungsten fixture. So you'll likely need to replace or augment your existing dimmer installation. We'll talk about the options a little later, but for now, just know that LEDs need non-dimmed power. So what makes LEDs different? First up, LEDs are complex devices made up of LED arrays, user interfaces, processors, optics, and cooling systems, usually fans. And keeping all of that running is a switch mode power supply, which is why it needs to have constant power. Switch mode power supplies have a lot of benefits, which is why they're used, but there are some negatives that can impact you, the user. Switch mode power supplies are capacitive loads, and as such have quite a large inrush current. This is an incredibly short surge of surprisingly high current at the instant you turn the power on. Think of it a bit like water rushing to fill up an empty hosepipe, but it happens in 1/100th of a second. Now this current can be many, many times the operating current of the luminaires, sometimes as much as 65 times higher, and it pretty much happens in the first mains cycle after you turn it on. In this image, the yellow is showing the supply voltage and the green the current, which spikes and then normalizes. For a ColorSource Spot Junior, which is a maximum power draw of about 160 watts, or 0.7 amps at 230 volts, the inrush over the first half cycle of mains power is 45 amps. Put 14 ColorSource Spot Junior fixtures on a single 230 volt circuit, and they'll pull just under 9.8 amps at full output, easily inside the capability of a 10 amp breaker. But the combined inrush will be a whopping 630 amps. This means your power supply and breakers must be able to deal with the combined inrush of all the fixtures on the circuit. And that includes upstream breakers too. So not only does each circuit's breaker need to cope with its individual load, you also need to be wary of the breaker that is covering the incomer to the distribution board to make sure it can handle the total inrush. There is some good news in that because the inrush is very short, you don't need to size the breaker to handle that inrush current as a continuous load. But you do need to make sure that the breaker you're using is appropriate for these sort of transient loads. The other good news is that breaker manufacturers and electrical engineers know all about inrush. So most breakers in the 230 volt parts of the world are labeled with a curve type, and that shows how they respond to inrush. Most theater racks will have a C or a D curve breaker, which will have slower response times to allow for inrush current. But it's important to know the circuit you're going to use will be able to cope. So, how does this momentary spike actually affect you? Imagine a scenario where an engineer was commissioning some fixtures in a lecture theatre that has moved their switched tungsten fixtures over to LED. They decided to reuse their previous 5 kilowatt circuit as it had more than enough current capacity for their new LED fixtures. One by one, they carefully unbox, rig, plug in, and focus their new LED fixtures until all 20 units were working beautifully. Then they turned off the circuit and went home, feeling proud of a job well done. The next morning, they called their boss in to show off their handiwork, but every time they tried to turn on the power, it would just trip instantly. One way to mitigate the impact of inrush from your entire rig without having to reinstall new breakers is to make sure that you're not turning everything on in one go. By plugging them in one by one, they'd been limiting the overall peak inrush current, spreading it out over a longer time period. But trying to switch them all on together was just too much for that breaker to handle. This is an important thing to think about, as you could say that to solve this, they just need to unplug some fixtures and plug them in by hand each day, which might work just fine. But what happens when you don't have that manual control of the turn-on process? What happens if, during an event, there's a power cut, a blackout, and then a little later, the power is restored? That circuit's just going to trip instantly again as it tries to energize all of those fixtures in one go. Adding in a power control system would help. This could be as simple as latching contactors that you turn on one by one. Some power controllers even allow for an automatic switching delay to help deal with inrush. This could be a fixed time delay. You may have this sort of thing already for turning on your sound system in the right order, which turns on a circuit every second or so. There are some products, like our distributed color source relay units, which are seeded with a random delay. That means multiple color source relays in a rig will turn on a few milliseconds apart from each other, and they switch at the zero cross point to further limit that inrush. They're particularly useful if you're touring LEDs into other people's venues. Power sequencing could also solve that issue with what happens after a power cut, assuming that on restoration of power, they go through their phased switch-on process, rather than just hold last look. So you need to be thinking about both controlled switch-ons and those you don't have control over. Ask yourself, what happens after a power cut? The second issue with switch mode power supplies, mostly seen in regions where RCDs or GFCIs are required, concerns earth leakage. Earth leakage is a phenomenon where smoothing capacitors in the fixture, which are thereby designed to reduce the interference experienced elsewhere on the main supply by rapid switching in a PSU, those capacitors leak a small amount of current to ground. These small leakages, in the region of 1 milliamp from each fixture, adds up across the circuit or the installation and can cause an RCD to trip even though nothing has actually gone wrong. In Europe, most RCDs in use for final circuit protection are required to be 30 milliamps. So you might think that given an approximate 1 milliamp per fixture, you can probably get about 30 fixtures on a single 30 milliamp RCD before you see problems. But that's not how RCD ratings work. A 30 milliamp RCD is given that rating by conforming to the following specification. If 30 milliamp of earth leakage current is present, the device must trip. If 15 milliamp or less of earth leakage current is present, the device must not trip. There is nothing in the specification that says what must happen in the area between 15 and 30. That's left to the manufacturer and allows for component tolerances. Because of this, the guide is for a maximum 30% loading of an RCD with continuous leakage currents. So you're probably now looking at about 10 fixtures per RCD as the most you'll be able to get away with. It's also important to note that some local regulations may stipulate that the maximum allowable continuous earth leakage per circuit could be considerably lower than that 30% rating. So please check what your local regulations say. And that's assuming that you have one RCD or RCBO per circuit and not shared across multiple channels. After looking at the electrical characteristics of the fixtures, we've concluded that a 15 amp C-curve breaker on a 30 milliamp RCD on our circuit, we can confidently plug in about 10 fixtures and they'll all work nicely. But should you plug that many in? Now, unfortunately, that's something that only you can decide, as it comes down to the question of how many fixtures can I afford to lose before I have to call a stop to the performance. Imagine if you had all of your front of house fixtures on one circuit and one fixture develops a fault and the breaker trips. You'd lose all 10 fixtures. Can the show continue without any front light? If they were plugged in, one per circuit, then you might be able to get by if you lost one. But per fixture power infrastructure can be expensive. So you need to try and strike the right balance. Maybe you should plug things up in a way to better deal with that fault scenario. Maybe spreading those fixtures over 2 or more circuits would give you better resilience. For example, if you have a group of fixtures lighting a cyclorama or a backdrop, you might choose to wire them up on 2 circuits. But rather than grouping them as left and right, which would be easier when rigging the cabling on the truss, consider wiring every second fixture on circuit A and the rest on circuit B. This means if you lose one circuit, you still have coverage of the whole cyc in the event of a failure. Yes, it may be half the brightness, but it's going to be better than a half dark and a half bright cyc, and it might allow you to just keep the show going. Your counterpoint to this might be, it is absolutely okay for me to lose large chunks of my rig in one go. It's a low stakes environment where pausing to find the fault and resetting the breaker is perfectly acceptable. And you might well be right. For example, if you have a lighting rig used in a drama classroom or a rehearsal space, there are totally different things to think about compared with a 1,000-seat professional venue where everyone has paid hundreds for their tickets. Only you are in a position to make that final judgment of what is acceptable for your setup. But please do think about it. Also, be comforted that LED fixtures are less prone to failure during a show than tungsten. There's no lamp to blow when you bump things up to full intensity. So the planning for failures mid-show is preparing for really rare scenarios. So, what do you use to distribute your power to these new fixtures? There are several options available. The first and most tempting is just using your existing dimmers, set them to full intensity. This isn't a great idea, as even at full, most dimmers do not pass a pure sine wave, especially if they have any form of regulation in them to manage that output voltage. It might work, but it will likely shorten the life of the power supply in your fixture, if that power supply is not designed to be mains dimmable. And it requires you to ensure that no one can accidentally dim that channel. The simplest new piece of infrastructure is a standard distribution board. But remember that standard breakers are not suitable for switching on and off appliances. So having some form of switches or contactors that allow you to switch the rig on or off is important, especially as you want to be able to switch things on bit by bit to limit the inrush current, remember? And switching fixtures off at the end of each day is a good thing to do, as unlike tungsten, at 0% intensity, they're still drawing a couple of watts of power. The next option up is through power, a dimmer and hard power in one package, sometimes with a remote switchable relay. These are a great option for venues that still plan to use some tungsten, but be aware that not all through power options are created equally. Bypass-only options that leave the dimmer choke in the circuit can cause the same problems as a dimmer set to full, and bypass-only options without switching capability suffers from the same issues as a straight distribution board when it comes to limiting inrush at switch on or after a power cut. Finally, there are power control relays, which are just DMX-controlled switches. Again, there are different types available. It's important that you go with air gap relays that physically open and close a switch rather than solid-state relays. Solid-state relays can sometimes have trouble turning off very low power loads, like that 2-watt standby load presented by an LED fixture. Both relay and through power options might be available as option cards for your existing dimmers. So you may only need to change some cards or modules rather than having an entirely new power control rack installed. So do contact your local dealer or installer who can help you advise the most efficient way forwards. Moving to LED isn't just about buying new fixtures. You will need to think about power and data distribution. And as with any new technology, you will need to adjust your workflows. But the creative possibilities available now are incredible. Don't be afraid of making the switch to LED, but remember to think about your power needs. Think about how you will energize and power down your rig. Think about the number of things plugged into each circuit, and think about how you will handle the fault conditions that we've talked about. What is affected when a single breaker trips? What happens after a power cut? Because in the unlikely event that something does go wrong, just this little bit of thinking now could save your show. Thank you.